In May 2021, NASA confirmed something about the emptiness of interstellar space that no scientist had ever been able to measure directly before, because no instrument had ever actually been sitting inside that emptiness long enough to listen. Voyager 1, more than 14 billion miles from Earth, had been quietly picking up a faint, continuous signal since 2017, a narrow, steady tone humming in the space between the stars, present at every single moment, whether or not anything dramatic was actually happening nearby. It had been there for years before anyone noticed it, buried in data that had already been collected, transmitted, and archived, waiting patiently to be found by anyone patient enough to go back and look for something nobody had specifically been searching for. Space, according to nearly every model built before this discovery, was supposed to be still out there, a thin, largely silent vacuum with nothing much going on between the rare, violent events that occasionally disturbed it. Voyager 1 found something different. It found that interstellar space has a sound of its own, a persistent, ever-present hum that never actually stops. This is the story of that hum, one of the strangest and most quietly profound discoveries to come out of the entire Voyager mission, and what it reveals about a universe that turns out to be far less empty and far more alive than the space between the stars was ever assumed to be. To understand why this discovery mattered so much, you first need to understand what Voyager 1 was actually listening for, and why nobody had ever managed to hear it clearly before. Voyager 1 launched in September 1977, and after its historic flybys of Jupiter and Saturn in the years that followed, spent decades pushing steadily outward through our solar system's outer reaches. In August 2012, it became the first human-made object in history to cross the heliopause and enter true interstellar space, moving beyond the reach of the sun's own protective bubble for good, a milestone confirmed more than a year after it actually happened, once researchers had gathered enough supporting evidence to be certain. Ever since that crossing, one of the spacecraft's instruments, called the plasma wave system, has continued operating, listening for electrical oscillations in the extremely thin, extremely cold plasma drifting through the space around it, the diffuse mixture of charged particles that fills the vast gaps between star systems throughout the galaxy. That plasma is almost unimaginably sparse, far thinner than the best vacuum any laboratory on Earth has ever produced, containing in some regions fewer than 1 particle per cubic centimeter of space, and for years, the only way scientists had of measuring its density involved a stroke of luck, waiting for a specific, violent event to occur nearby, and light the whole plasma up briefly enough to actually detect it. That event is called a coronal mass ejection, an enormous eruption of charged particles and magnetic field blasted outward from the sun's surface, sometimes containing billions of tons of material, traveling for months across the vast distances of the outer solar system before finally reaching the distant region of space where Voyager 1 now sits. When one of these solar eruptions eventually catches up to the spacecraft, it slams into the surrounding interstellar plasma and triggers a shockwave, and that shockwave excites the plasma into a brief detectable oscillation, electrons within the plasma vibrating at a specific frequency directly tied to how densely packed they are. A burst of electrical activity strong enough for Voyager 1's instruments to register clearly, and precise enough that researchers can work backward from the oscillation frequency to calculate the exact electron density of the surrounding plasma at that moment. Since Voyager 1 first crossed into interstellar space, scientists have identified 8 of these plasma oscillation events, each one lasting anywhere from a few days to as long as a full year, and each one giving researchers a valuable but frustratingly temporary window into the density of the plasma surrounding the spacecraft at that specific moment. Between those events, for years at a time, the plasma around Voyager 1 appeared to fall silent, its density essentially unmeasurable, waiting for the next distant solar eruption to happen to pass through and briefly illuminate it again, leaving researchers with long, frustrating gaps in an otherwise valuable dataset. Gaps that could stretch for a year or more between one usable measurement and the next. That gap in the data, long, uncertain stretches of time between one lucky solar-triggered event and the next, is exactly what a team of researchers led by Stella Koch-Ocker, a doctoral student in astronomy at Cornell University, set out to close. Rather than waiting for the next dramatic eruption to arrive from the sun, Ocker and her colleagues went back through years of accumulated data from Voyager 1's plasma wave system, searching specifically for anything faint and continuous sitting quietly in between the known plasma oscillation events, a background signal that might have been sitting there the entire time, simply too weak to have been noticed against everything else. The instrument was picking up a painstaking process of combing through years of low-level instrument readings that most researchers would have previously dismissed as unremarkable background noise, not worth the effort of close examination. They found it, starting in 2017 and continuing steadily onward from that point. The team identified a persistent narrowband plasma wave emission, a signal fundamentally different in character from the sharp, dramatic oscillations triggered by solar eruptions. This new signal was weak, monotone, and confined to an extremely narrow slice of frequency, centered around 3 kHz with a bandwidth of only about 40 Hz. A signal so faint and so specific that it had gone entirely unnoticed in previous analyses of the same underlying data, hiding in plain sight inside years of archived transmissions that researchers had already examined many times over for other purposes. Ocker described what they had actually found in strikingly plain, evocative language. This, she explained, was the faint, persistent hum of interstellar gas itself, quiet and monotone precisely because it occupied such a narrow frequency bandwidth, an ambient, ever-present signature of the plasma surrounding the spacecraft, entirely independent of whatever dramatic solar activity happened to be passing through at any given moment. The findings were published in the journal Nature Astronomy on May 10, 2021, under the direct, unadorned title, Persistent Plasma Waves in Interstellar Space, detected by Voyager 1, a paper that would go on to reshape how researchers think about measuring the density of the space between stars going forward. The significance of that distinction is worth sitting with directly because it is the entire reason this discovery mattered so much to the broader field of astrophysics. Every previous measurement of interstellar plasma density made by Voyager 1 had depended on a loud, disruptive event, a shock wave from the sun forcing the plasma to reveal its properties through sheer violence, an approach that gave researchers accurate but sporadic snapshots, useful but incomplete, like trying to understand an entire ongoing conversation by catching only the occasional shout. This new signal required no such disruption at all. It was simply always there, a steady background presence in the plasma itself, humming quietly regardless of whether anything else was happening nearby. James Cordes, the senior astronomer on Ocker's research team at Cornell, offered a vivid comparison to help explain the difference. The interstellar medium, he said, behaves something like a quiet, gentle rain, a constant, low-level presence, and a solar-triggered plasma oscillation event is like catching a burst of lightning during a passing thunderstorm, dramatic and unmistakable while it lasts, but temporary, fading back into the same quiet rain once the storm itself has passed. Cordes went further still, describing the moment of realizing this signal was actually there, present continuously, as something almost startling in its own right, a background presence that had simply been waiting patiently for someone to notice it was singing the entire time. That gentle, persistent rain turned out to be scientifically valuable in a way the dramatic lightning bursts never could be on their own. Because the new signal was continuous rather than sporadic, Ocker's team was able to use it to build the first steadily sampled measurement of interstellar plasma density ever assembled, tracking changes across roughly 10 astronomical units of space with remarkably fine resolution, sampling the surrounding plasma on average every 0.03 astronomical units as Voyager 1 continued its steady outward journey. Nothing like that continuous a record had ever existed before, because nothing had ever given researchers a signal reliable enough and persistent enough to actually build one. Previous measurements, reliant entirely on rare solar-triggered events, had produced only a handful of individual data points scattered unevenly across years of travel. This new signal filled in the gaps between those points with a density and a consistency nobody had thought was even possible to obtain from this specific instrument. What that continuous record revealed was its own kind of quiet surprise. Tracing the signal back across the full data set, researchers found that the electron density surrounding Voyager 1 had begun rising in 2013, not long after the spacecraft's initial crossing into interstellar space, and had climbed steadily until reaching a plateau around the middle of 2015, an increase amounting to roughly a 40-fold rise in density over that period, a change far larger than most researchers had anticipated, finding in a region of space assumed to be relatively uniform. From that point onward, through the full stretch of data examined, running until early 2020, the density remained within a broadly similar range, fluctuating in smaller, more localized ways that the team was able to trace directly to interstellar turbulence, small-scale variations in the plasma occurring across distances measured in individual astronomical units, structure that had simply never been visible before at this level of detail. That structure matters because it echoes findings that would later be confirmed independently when Voyager 2 made its own crossing into interstellar space in 2018, and researchers found a broadly similar transition in fluctuation behavior in its data as well, a separate spacecraft in a completely different part of the sky, tracing out a comparable pattern of turbulent structure in the very local interstellar medium. Ocker described the value of this new dataset directly, explaining that it allowed her team to regularly sample the density over the longest continuous stretch of space they had ever had access to. producing what she called the most complete map yet assembled of the density of the interstellar medium as observed by Voyager. There is still a genuine, unresolved scientific question sitting at the center of this discovery, and researchers involved in the work have been careful not to overstate how settled the underlying physics actually is. Exactly what physical mechanism produces this persistent narrowband hum in the first place remains an open question. One possibility is that it results from thermally excited plasma oscillations, natural vibrations arising simply from the ambient temperature and motion of the plasma itself, a process that would fit comfortably within existing theoretical frameworks without requiring anything particularly exotic to explain it. Essentially, electrons jostling gently against one another due to nothing more than the residual heat left over in the plasma from its own formation. A second possibility is a phenomenon called quasi-thermal noise, a related but physically distinct process that would carry subtly different information about the density and temperature of the surrounding plasma, arising instead from the statistical fluctuations inherent in any collection of charged particles moving randomly through space, and that would require researchers to refine certain existing assumptions about exactly how interstellar plasma behaves at this level of detail. The distinction between the two is not merely academic. Each explanation implies a slightly different underlying temperature and composition for the plasma itself, and getting that distinction right matters directly for how accurately future models of the interstellar medium can predict what any future spacecraft or any future mission specifically designed to study this region might actually encounter out there. Distinguishing clearly between these two explanations, the research team has noted, will likely require either additional data collected directly by Voyager 1 itself in the years ahead, or an entirely new mission specifically designed to study the interstellar medium with instruments built for exactly this kind of precise measurement, a mission that, as of right now, does not yet exist and has not yet been funded. Beyond the specific mechanism producing the signal, the discovery carries a broader significance for understanding the region of space immediately surrounding our own solar system. This continuous plasma density record helps researchers understand precisely how the interstellar medium interacts with the outer edge of the Sun's own heliosphere, the same protective bubble that shields Earth and every other planet in our solar system from a significant portion of the harsher radiation constantly streaming in from elsewhere in the galaxy. That bubble is not a passive, unchanging wall. It expands and contracts in response to the Sun's own roughly 11-year cycle of rising and falling activity. And it is simultaneously being pressed on from the outside by the surrounding interstellar medium, a two-sided negotiation playing out continuously across billions of miles of space. One side we can observe fairly well from Earth-based instruments, and the other side we can now, for the first time, actually listen to directly, in something close to real time, thanks to this exact signal. Ocker has noted that this kind of ongoing measurement helps scientists understand how that protective bubble is shaped and modified by the surrounding interstellar environment pressing in against it from every direction. Information that feeds directly into models of how well and how consistently that shield has actually protected the solar system across deep timescales that matter enormously when considering how cosmic radiation exposure has varied throughout the entire history of life on Earth. There's also something worth appreciating about the sheer engineering improbability sitting underneath this entire discovery. Voyager 1 was designed and built in the 1970s, using instruments engineered specifically to study the environment near Jupiter and Saturn, planets it would only ever visit for a matter of days each, decades before anyone involved in that original design. Work could have reasonably anticipated the spacecraft would still be operational and still returning genuinely novel scientific data. More than 4 decades later, from a region of space, its original instruments were never specifically built to study. The plasma wave system itself was designed to detect the specific kinds of electrical activity expected. Near the giant planets it flew past in its first few years, activity involving auroras, radio emissions, and interactions with each planet's own magnetosphere. Not a faint, continuous hum drifting through the near vacuum of true interstellar space, a use case that simply did not exist as a concept when the instrument was originally built. Ocker herself has described the achievement in almost reverent terms, calling it a genuine testament to the amazing engineering of the Voyager spacecraft itself, an unplanned scientific gift delivered by hardware that was simply never expected to still be working this long, or to still be capable of revealing something this subtle about the true nature of the space between the stars. That persistence carries its own kind of significance looking forward, too. Because this new signal does not depend on the unpredictable timing of solar eruptions, researchers now have reason to believe Voyager 1 can continue tracking the density of the interstellar medium around it on an ongoing, essentially continuous basis, for as long as the spacecraft's instruments remain functional and its dwindling power supply allows the plasma wave system to keep operating. That is not a guarantee measured in decades, Voyager 1's power output continues shrinking every year as its radioisotope generators decay, and mission engineers have already been forced to permanently shut down several of its other scientific instruments simply to keep the spacecraft transmitting at all. The plasma wave system remains one of the small handfuls still running. In every additional year, it survives, adds another stretch to what is already the longest, most detailed, most continuously sampled record of interstellar plasma density ever assembled by any instrument in the history of astronomy, a record built entirely from a signal so faint that it sat completely unnoticed in the spacecraft's own data for years before anyone thought to go looking for it specifically. Sit with the basic strangeness of that for a moment. The space between the stars, the vast, largely empty gulf that separates our solar system from everything else in the galaxy, was long assumed to be close to silent, a thin, largely inert medium punctuated only by rare, violent events, useful mainly as a backdrop against which more interesting things elsewhere in the universe could be studied. Voyager 1 found instead that it hums, constantly, quietly, at every single moment whether or not anything dramatic happens to be passing through, a background note running underneath everything else happening in that vast, cold darkness, audible only because one aging spacecraft, built with technology from another era entirely, happened to be sitting there long enough and sensitively enough to finally pick it up. It is worth remembering, too, that this signal was not something Voyager 1's instruments were specifically searching for when the data was first collected. It had been sitting there, quietly recorded, transmitted across billions of miles, and archived on Earth for years, indistinguishable from background noise to anyone who was not specifically looking for a continuous, narrowband tone buried underneath everything else the plasma waves system had ever picked up. It took a graduate student, years after the relevant data had already been collected, going back through an existing archive, with a genuinely open question in mind, to actually notice that the hum was there at all. That is its own quiet lesson about how much may still be hiding, fully recorded and fully available inside data that has already been collected and filed away, waiting simply for someone patient enough and curious enough to go back and actually listen for something nobody thought to search for the first time around. There's a real chance this same basic approach, searching patiently through existing archives rather than waiting exclusively for new, dramatic events, could reveal further signals buried in Voyager 1's data in the years ahead. Additional structure in the interstellar medium that nobody has yet thought to specifically look for, hiding in transmissions that have already reached Earth and are simply sitting, unexamined in this particular way, in an archive somewhere, waiting for the next person curious enough to ask a new question of old data. If this is the kind of story you want more of, subscribe. And let me know in the comments whether you think interstellar space is stranger or quieter than you originally imagined.